So once we form these enolates, what kinds of reactions can they be used for? And probably the most common one is an alkylation reaction. Now, this alkylation reaction, while it's going to seem new, it's going to be a new reaction in terms of the nucleophile-electrophile pair. If you look carefully at it, you're going to notice that it's a reaction we've already learned. So once we form the enolate, we can add an electrophile such as any alkyl halide. Something like methyl iodide works very, very well. The enolate reacts by the carbonyl reforming, the pi electrons attacking carbon, and kicking out iodine. And so we form this new carbon-carbon bond, adding the alkyl group from the alkyl halide to the alpha carbon. Now when I say this should be a familiar reaction to us, what reaction is this? Well, this is just another example of an SN2 reaction. And so because of that, this reaction is subject to all of the same constraints that we've learned and talked about for SN2 reactions. So if you want to use something like benzyl iodide as your electrophile, that'll work extremely well. And whatever nucleophile, whatever enolate you formed, we'll add it in. But other electrophiles, ones that we would have said are bad for SN2, are also going to be bad for these alkylation reactions. So if you tried something such as tert-butyl iodide, just like it doesn't work for SN2, it's not going to work for this reaction because it's too sterically hindered. Same thing with one like this. Yes, it can work, but because you've got this neighboring hydrogen, you're going to get competition from elimination. So here we've used as an example a ketone to form our enolate for this reaction. You can use other carbonyls, you can use esters, and then because an ester will form an enolate in the same way. And then it can function as a nucleophile. And then one that might seem quite a bit different, but can also be used, is you can use a nitrile to form an enolate. Well, not really an enolate here because there's no oxygen, but the same type of reaction. That pi system on the carbon from the nitrogen can help support the negative charge the same way that the carbonyl does. Now, the one you might be surprised by are aldehydes. Aldehydes, it turns out, don't work well for alkylation reactions at all. And the reason for that is, we think about aldehydes as being very reactive. And it turns out that's actually the problem. The problem is they're a little bit too reactive. And so if you're able to make an enolate out of an aldehyde, which you can do very easily, the problem becomes that once you've done that, whatever aldehyde is left over is also a very good electrophile. And so you often end up with the aldehyde reacting with itself. Now, that's not a terrible thing. In fact, we'll learn a reaction in the next chapter known as the aldol condensation, which takes advantage of that property. The other carbonyl that can be very difficult to alkylate is a carboxylic acid. And the carboxylic acid is difficult to alkylate because if we add a strong base, such as LDA, to it, well, we have a hydrogen that's more acidic than the alpha hydrogen, that being the carboxylic acid one. And instead of making an enolate, our base here will just deprotonate the acid and form a carboxylate salt. So what do we do if we wanted to be able to react with a carboxylic acid? Well, in some situations we might just basically be out of luck. But if we're trying to do something simple like acetic acid, there's some actually pretty easy ways around it. And the way that we get around it most commonly is using what's known as a malonic ester synthesis. So the malonic ester synthesis takes an ester, which is derived from malonic acid. So basically take malonic acid and stick those two R groups on there. And now if you add a base to it, you're not going to end up with problems with deprotonating the carboxylic acid because right now it's not there. So if we add a base, we are very easily going to remove that central proton. That central proton is extremely acidic because it's resonance stabilized by both carbonyls. At that point, we can add an alkyl halide to it. Attacks, we get our alpha alkylation. At this point, the alkylation piece of the reaction is done. But what happens if we add acid to it and heat it? Well, we know that an ester can hydrolyze under acidic conditions. And so both of those esters, under acidic conditions, especially with heat, will get converted back to their carboxylic acids. So now we've taken basically malonic acid and alkylated it. But the reaction, turns out, isn't done yet. Because if we notice, and this is why we have to use malonic acid specifically, that hydrogen on the carboxylic acid is 6 atoms away from the other carbonyl. And so under these conditions, under heat and acid, the carbonyl will grab that, those electrons shift down, we break this carbon-carbon bond, and this step is completely irreversible because if you notice here, this is the piece that we're kicking out. It's carbon dioxide, goes away as a gas. And we're left with this enol. And this enol here can then tautomerize to form the carboxylic acid. And so now what it looks like we've done is it looks like we've managed to alkylate acetic acid. Now, we can't alkylate acetic acid under these kinds of conditions easily because acetic acid will just deprotonate. But by using this reaction, we've done the equivalent thing to alkylating acetic acid and formed that product. So again, as I mentioned, most reactions when it comes to alpha substitution reactions prefer to use acidic conditions. I'm sorry, prefer to use basic conditions. There's one major exception to that, and that's the idea of alpha halogenation. In other words, what if we wanted to take our carbonyl and put a bromine next to the carbonyl. How would we do that? As I said, this is the one major reaction that prefers acidic conditions. And so the way that we do that is using a strong acid such as HBr and bromine, carbonyl protonates, as it always does under strongly acidic conditions. That activates it so that we can easily remove that alpha hydrogen and form an enolate. That enol. The enol we know is a nucleophile. We have an electrophile present in bromine, and so the enol here can attack bromine. And then if we lose that hydrogen, we form our product. So why is it that we have to use acidic conditions here? Why can't we use basic conditions? Well, it turns out if you use basic conditions, you actually get a completely different reaction. So what reaction do you end up with base? You end up with a reaction known as the haloform reaction. So the haloform reaction uses sodium hydroxide and bromine. And in the first couple steps that aren't at all surprising, we start by forming an enolate. Then that enolate, just like you saw in the previous reaction, will attack bromine. Giving us this product. And at this point, everything looks fine. Looks like we've done exactly the same thing we did under acidic conditions. The problem here is we've now added an electron withdrawing group to our alpha carbon. What will that do as a result? Well, as a result, it makes that alpha carbon even more acidic. In other words, we've now formed a product that is more acidic than our starting material was. So what'll be the result? The reaction happens again. Adding a second bromine. Now, if one bromine made it more reactive, the second bromine even more so. And so the reaction happens a third time. And so now on that methyl group, we've replaced all three hydrogens with bromines. Now, that's a very electron withdrawing group. And if there's, as long as there's still hydroxide present, it'll encourage hydroxide to attack the carbonyl. Now, we've seen plenty of cases of hydroxide attacking carbonyls before, and we always say that reaction is not a big deal because it's very reversible and actually favors the starting material. Unless we have a good leaving group. And CBr3-, because it's got all of those electron withdrawing bromines, is good enough to function as a leaving group. And so the O- kicks out CBr3, and we end up with a carboxylic acid plus the carbon tribromide anion. That'll deprotonate the acid, giving us a carboxylate salt, which upon quenching with acid gives us our carboxylic acid back. So the reason that we can't use basic conditions is because, as you can see here, something completely different happens. And what is that completely different thing that happens? Well, we're able to react multiple times, and because it reacts multiple times, instead of ending up with a ketone, we go all the way to a carboxylic acid. So a reaction that is useful for its own reasons, but not as a halogenation reaction.